I do wonder, had you, if budget was not a question, had you actually tested that and used the frontier models, the finest frontier models, as teachers in this categorical experiment, do you think the best teacher would have been the most expensive, largest, best performing frontier model? Okay, so we started off with some woodworking and some quick physics exercises, and we're ready to go, I guess. Mm-hmm. Okay, well, thanks again. I'll quickly introduce myself, Ahmed Bashir, leading engineering at DevRev, and we have with us
Alex Dimakis. I'm a co-founder of Bespoke Labs and a professor in UC Berkeley.
Outstanding. Well, welcome, Professor. Should I call you Professor here? Or?
No.
Alex? Or?
Call me Alex.
Okay, Alex, thank you. So let's start with something that's near and dear to your heart. I know you posted about this on LinkedIn. So last few months, you guys have been hard at work, open thoughts, OpenThinker. Tell us some more.
Yes, so this project started when DeepSeek R1 came out, which was the first reasoning model that showed its traces, and it showed to the world how reasoning works. It also showed that it's actually possible to endow reasoning to a non-reasoning model if you simply SFT on a few thousand reasoning traces. So reasoning, just to make sure we're on the same page on that, is just chains of thought, and chains of thought existed before, but the previous chains of thought were sequential and were always correct, right? If you asked a model to answer what's 5 plus 5, it will say, step 1, I do this, step 2, I do this, step 3, the answer is that, and all those steps were always correct. Whereas a reasoning chain of thought has the signatures of backtracking, verification, solving the same problem multiple times, questioning itself, and so on. So the challenge was, how do we get a few thousand of those reasoning traces that are richer, backtracking, dynamic thinking traces? And the moment we have them, and they're reasonably close to the base model, so that the probability of the model speaking those words cannot be tremendously low. But if it is reasonably close to the base model, then with SFT, you can convert a non-reasoning model like a Llama 3.1, 8B, or a Quen 2.5 into a reasoning model. And the definition of reasoning is you score well on the reasoning benchmarks like AMY, Math 500, and so on. So overall, the thing that we all realized was the data was the hidden missing ingredient, because DeepSeek R1 released the weights, but it didn't release the data set.
Right.
So that's where we said, okay, we have to create a reasoning data set. And we created Open Thoughts. The first one was 100,000 questions and answers. And a few days ago, we released Open Thoughts 3, which is 1.2 million questions and answers with reasoning traces that have been curated, verified, filtered in a very thorough process. And we also released a model called OpenThinker 3 that is the best reasoning model right now at its size with open data. Overall, we think that the other important value of our research has been the ablations, the different things we tried, and we measure how much each of the attempts in filtering questions, filtering answers, selecting different pools of sources affected the results. And that involved more than 1,000 ablation experiments that are described in our paper, which is a 70-page paper that we released a few days ago. That's called Open Thoughts.
Yeah, absolutely. So, I mean, I went through, I didn't read the entire thing, but I saw that you had these 5 important findings. Can you maybe just walk us through some of those?
Yes. So the first general finding is that synthetic question generation is very effective. So that is something that we thought that there's a big gap between human-generated data and synthetically generated, but just with a little bit of simple prompting techniques and a few in-context examples, LLMs are very capable of producing synthetic questions that are very good. That was one of the findings. Another one in general was that question filtering techniques matter a lot and help a lot, whereas answer verification techniques seem to make things worse. So verification made things worse in the answers, and the reason we think it made things worse is because when you throw away the things you cannot verify, you're actually changing the distribution of the answers. For example, we could not verify proofs easily. So
Right.
somebody would say, let's throw away all the proofs, but now the model has never seen proofs and it performs worse.
Yeah, and obviously the distribution changes that it's typically the harder things that are harder to verify. And so if you throw them all away, you're creating a bias.
Exactly. So we saw that many of the verification techniques created biases that were not obvious and hurt performance. So the other...
Well, before we move on, because obviously companies like us, DevRev, we're obviously looking into post-training in a big way, and we're working with you guys as well on this. There's this huge push towards generator verifier, right? So sort of the two sides of the same coin in terms of doing post-training. So you have to do a really, really good job of generating synthetic data and curating synthetic data. But then you also have to do a really, really good job of verification. But here you're talking about how verification is somewhat overrated, or how would you describe that?
For SFT, in the SFT part, verification was not effective in the OpenThoughts experiments. This surprised us. Verification is absolutely essential in a reinforcement learning setting.
And in SFT, obviously, there's the rejection sampling, and a lot of times rejection sampling is on the basis of a verifier.
Yes.
So would you say here that your finding is that doing a little less rejection sampling is actually yielding better results?
In our experiments, surprisingly, we had three domains. We had coding, math, and science.
Okay.
And in all three domains, which had separate ablations and separate question selection, separate verification processes, in all the experiments, verification of the answers either had no significant benefit or actually made things worse.
Okay.
Which was very surprising, and I think it is because it was changing the distribution.
Okay. Wow, that's interesting. Now, obviously, that's an important finding. Now, I'll just ask you a question on the basis of your academic interests. Is that a finding that you would now try to double click into? And so is there going to be a follow-up here when you get to the next iteration of OpenThoughts and OpenThinker? Are you going to try to double down on this? And if so, what does that look like?
Great. So the next step in our research project, and also the next step in all post-training pipelines, is reinforcement learning. Mm-hmm. So the OpenThoughts project focused on, let's create the best SFT dataset, see how far we can go. Surprisingly, we were able to go very, very far and beat models that have been even SFT and RL, reinforcement learned, improved. So usually RL gives you a 5% or 7%, depending on the benchmark, last mile.
Right.
But you always have to do SFT first to get the model at a good capability.
Right.
So we thought we will just focus on the data curation for SFT, see how far that goes, and then the next step would be to do reinforcement learning, which is what we want to do. And there you absolutely need verifiers because that's where your rewards are coming from. But surprisingly, if you have good teacher models, which is another finding that I want to dive into.
Yeah, we'll get there.
Yes, if you have good teachers, verification didn't show benefits in all our experiments, yes.
Very interesting. Now, you also talked about how generating multiple answers for the same question helps. This is great because, I mean, at some point you're talking about just squeezing more and more out of a smaller and smaller data set.
Yes. That's a very important finding and probably the most directly useful to anyone else doing data curation. We found that you can take the same question, that can be a math, coding or science question, and have the teacher model, which we tried DeepSeek R1, we tried Quen, QWQ, and we tried 5-4 reasoning as teachers.
Sure.
And we found that the same teacher can re-answer the question multiple times, so you expand your data set size. So we tried in our ablation, we said 1x, 2x, 4x, up 8x, 16x, and we stopped at 16x. We didn't go above that because all our ablations are done in 3 domains across multiple sources, so it was an extremely expensive set of experiments.
Of course.
And surprisingly, the 16x performed equally or the best. I think almost all our ablations on that. So it's possible that even 32 annotations are even further better. And this was in a 30,000 questions ablation.
Right.
But then we went up to 1 million and we still had 16x replication. So replication of using the same question multiple times is a very, very effective way to increase your SFT data set.
So if a person's working within a specific budget, so just to keep it simple, if you went from that 16 to, I don't know, 128, would you then allow yourself to maybe have a similar reduction in the number of questions that you actually ask, provided that you maintain some similar distribution in terms of difficulty? Would that be an experiment that you would do, or would you say, you know what, no, just leave the data set alone, the size of the data set remains the same, but if you have the budget, just try to get more answers? Like, how would you play that game?
Yeah, it's a great question. It depends if you are compute limited or if you are limited by the number of high quality questions.
Right.
The number one thing is the quality of the questions you select have to be close to your test distribution. That was the number one thing.
Right.
So if you're going to add more questions, but the questions you add are further away from your, then you should not do that. So we, in many of our ablations, we saw that adding more sources, that was another finding, adding more diverse questions actually seemed to hurt performance in all our experiments. We sorted basically, here's how our study works. We have multiple sources like Stack Exchange, CodeGolf, various sources of questions you can find. And then for each source, we randomly selected 30,000 questions. We created answers with DeepSeek R1 or QWQ. We SFT'd and we measured benchmarks. So that's the quality of a source.
Yeah.
So now you can score source number one, source number two, and now you create a million data set.
Right.
You could keep only the top one source or top two, or go top 8 and so on. We tried this ablation, and top 1 or top 2 was always performing the best. So you should pick do the smallest subset random sample, SFT, measure the performance in the benchmark, sort your sources like that, and take the first 1, 2, or 3, depending on the size of the sources. And by all means, then repeat the questions from the highest source. That's the recipe we propose in the paper.
I mean, it's almost like, cooking, right? It's like the Italian cooking methodology is source the best raw ingredients, like the finest salt and the greatest cheese, and you'll have the finest pasta, I guess.
Exactly.
So it remains the same. So it's the same idea.
The title actually is Data Recipes.
Yes, I know.
Yes.
Or maybe I should have used the Greek analogy. I don't know.
Yes.
But we'll figure it out. Teacher model selection. Tell me about that.
Right. So we expect that, so the teacher is the model that answers the questions and creates the reasoning traces.
Right.
There are very strong teachers like DeepSeek R1, QWQ, and 5.4.
Right.
We couldn't afford to use the frontier teachers like O3 and so on, because we needed to annotate thousands or actually millions of questions. So we tried those teachers, and we found that it's not always true that the best teacher is the best performing model is the best teacher. We found that, for example, R1, I guess, is not always the best, but even in domains where a model was outperforming another in a benchmark, it was not the strongest SFT teacher.
Right. And I mean, obviously, even in our own, like, you look at professional sports, right? The best players are not necessarily the best coaches, so on and so forth. But I do wonder, had you, if budget was not a question, had you actually tested that and used the frontier models, the finest frontier models, as teachers in this categorical experiment, do you think the best teacher would have been the most expensive, largest, best performing frontier model? So
we know that 5.4 reasoning was trained, this is a Microsoft model,
right,
and it was trained on O3 mini traces, I believe. And that is a very, very strong teacher. And that gave a very big boost to that. This is a 14 billion model that performs better than even 32B models. So yes, in general, if you have access to a very, very high performing teacher and you can create millions or maybe hundreds of thousands of questions and answers, if you pick your questions in distribution, right, it's going to be very, very strong. Let me ask you this. Obviously, you're saying that teacher selection is a major part of getting the best out of SFT or just post-training in general. So what is your guidance to somebody who obviously needs to do teacher selection? What would you say? Would you say that you've found, relatively speaking, what at least some of these larger models or popular models, what they look like as teachers? Or would you say in your very specific domain, given the very specific questions that you asked,
that you felt like this was sort of what you found in terms of the availability and the accessibility and also the performance of them as teachers? Or would you say that there's something more generic that you've uncovered here?
I think that the easiest thing to start, if you want reasoning, is to take already existing traces, which are already annotated. Start with that. If you have to create your own data set by a reasoning model, or if you're creating an agent, you need trajectories, which are another chapter we have to get into. But you're always better off starting with existing data sets and then creating your extra questions and answers with DeepSeek R1 or QWQ or Qwen 3. I think are the best teachers right now, or 5.4, subject to your budget.
Real quick on this topic, by the way, we could keep going on this paper specifically, but I've got to say, everybody, people who are in our domain, we do not want to use customer data to do any post-training, but we also want to have really, really good expert models for specific tasks, technical tasks, the type of tasks that you were, trying to do SFT on. What do you think this means? Because for people like us, it's music to our ears to hear that you can create synthetic data and have it be the absolute best way to curate data sets for the purposes of post-training. Do you believe that there's sort of an upper bound here in terms of what we can do, or do you feel like we're just going to get better and better at this?
I think if you have tasks that, this is for agentic workflows, if you have tasks that you can verify or measure something objective like performance or quality, I think that synthetic rollouts, which is the model trying to solve the problem, is going to give you very good performance if you throw enough compute at it.
We've talked about high quality sources again and again. How would you summarize or describe a high quality source? What does that look like?
I think it solves the task with sufficiently high probability is number one, and or you can verify it didn't solve the task and you can rerun it or take majority or have some way of making sure that you finally have traces that have solved the task. I think the general idea.
5 minutes ago, we also talked about certain questions where the answer could not be verified.
Right.
So, I mean, it's okay to leave that in there. In fact, it's better to leave some of that in there.
If it is close to the testing distribution. It may be, if it is not, so it's not obvious.
Right.
If it turns out that adding proofs was useful for Amy, which doesn't, Amy has a numerical answer. Every Amy problem has a numerical answer.
Sure.
But still including proofs helped in Amy. But if you tell me I have some other problem, I have some accounting problem, should I add legal data? The short answer is I don't know. You have to measure it. You have to train on this data set and see the performance on the benchmark.
Okay, sounds good. I want to move on and get to some other topics. And obviously, you and I have spent a lot of time talking about reasoning, post-training, and so on. Obviously, for everybody in the industry right now, reasoning, planning, thinking traces, this is the frontier that's gotten a lot of attention. But then on the other hand, there's been this very recent paper from Apple, and I know you've gone through it and I've perused it as well, where it's called the illusion of thinking. How do you, based on what you read, what do you think? I mean, basically what they're saying is, at least from my vantage point, is that thinking works up to a certain level of complexity, beyond which it's literally just chasing its tail.
Yes. I think that this paper, in addition to some others, like Alice in Wonderland, was one other example, another paper that came in my mind, that said that these models, we tend to think of them like humans, and sometimes we ask them a question, like Alex and Bob have Alex has 3 apples, Bob has 2 apples, how many apples do they have together? Which all the even non-reasoning models get, and then you change the names. So you create 100 variations of this problem, but you change the names, and 1 out of 50 or 1 out of 100, the model will make a mistake.
Right.
And that is very weird because we as humans say, how can it, then it doesn't truly know how to solve this simple math problem, because when the names were, Bob and Jahar or something, it made a mistake. So then they're like, okay, what's the robustness? Is it 1 in 100? And then you can keep adding roadblocks.
Right.
So make the problem hard. It's not like 5 apples. You can say the number of apples Alex has is the solution of this quadratic equation, and the number of apples Bob has came from this other simple puzzle. So you can build more complex puzzles.
Right.
that again, you would say, if a high school student can solve this little puzzle,
right,
they could plug this little puzzle in this other puzzle,
right,
and that's like the horizon in a way, like the number of steps. So if the model was truly reasoning, it would be able to solve a puzzle that has 5 or 6 or 7 steps of such nested roadblocks or complexity.
Sure.
But the models were failing, especially as you start changing both the names and the complexities. You have all these degrees of freedom. You will try, thousands of variations, and then you will make mistakes in 1%, 2%, depending on the model. And I think what's happening is the models are not thinking like humans. And I think we should not think of them as, it's not reasoning, because when I gave it the specific flavor of the problem, it failed and a human would not fail. I don't think we should think of them like humans. I think we should think of those as distributions of tasks, and if you train enough in a distribution, the model can be very, very good, outperform most humans.
Mm-hmm.
Now, if you change the distribution, usually you need to post-train the model again. So the models are not able to, if it's like you study for the SAT, now you take the LSAT, that's a different exam.
Of course.
Yeah. So we wouldn't be surprised if a human, who studied for the SAT did poorly on LSAT. So in a way, you should think of post-training as training for a test, and then it generalizes to other questions in the test, in the same distribution. So it doesn't overfit to the questions.
Right.
It overfits to the domain. But the domain is general enough that you can make very useful things. Basically, every job really has a domain that has, 99% of the problems can be solved, and then every once in a while something crazy, a computer explodes,
right,
and now you have to step outside of your normal job and be like, okay, you have to put out the fire. Now, I have never been trained to do that.
Yeah.
But that's okay. You can always think of an agent. For most situations, the agent can solve usual problems in distribution. If it gets out of distribution, it can escalate to a human. They're definitely not robust as the distribution is changing.
Right.
And that makes people think they're not reasoning. I don't think they're reasoning like humans, for sure.
Of course.
But they can solve a ton of problems, and that's what we should do with them.
Well, let me ask you this, because look, if you gave me a test and you said if Alice had 2 apples and Bob had 4 apples, how many Bob? You might say, I'll never make a mistake. But the reality is, if you gave me 100 of those questions,
right,
I might make a mistake every now and then. And probably, a lot of parents who would, if I was a student in school, they would say, double check your work.
Right.
Sampling. Right? So does that work in this case? So if I were to play this game and then instead of allowing the model, a trained model, post-trained model, to actually answer the question once, I actually asked it to answer the question twice or thrice. And let's just say the answer is always a numerical value.
Right.
Do you think it could get 100% right?
So that is a very good question. This is a method of inference time compute. That's taking majority of, which you can do, as you said, if the answers are numerical. And yes, there are plots in many papers that show your performance at 1, performance at 32, consensus at 64, or majority at 64, and yes, the performance goes up. Now, does it go up to 100%? No, as far as I know, for example, DeepSeek R1 had a 7B model, and I think majority at 64 of the 7B was better than the big DeepSeek, the teacher. The teacher was a 600, B parameter. It was a very big MOE. But yes, a 7B majority, I think at 64, outperforms a much bigger model, which is showing the power of inference time compute. But you ask, if I let the majority at 1,000, will I get to 99%, in naming? I think not. I think it seems to saturate.
Okay.
But it definitely gives a very large benefit.
Okay. Look, if obviously everything has some level of, you're never gonna, it's asymptotic at some point.
Yes.
That's just the way it is. I think we got to this where you talked about giving your budget, giving compute time, and so on and so forth. Let's just talk a little bit about long-running tasks, because you talked about how many hurdles, right? If you change the names and you start to change the actual, compute model, change the names of the fruits, things like that, and you start to create more hurdles. It's just creating more and more context and you have to go through several steps to actually achieve the answer. When we talk about long-running tasks, obviously at some point you have to introduce some sort of a memory system or not. How do you think about this? Because with reasoning, people are going to expect not just more consistency, which is what we've been talking about, but they're also going to expect being able to satisfy and handle greater levels of complexity. So we're going to see 10x in complexity as well, where people are going to say, okay, you know what? You can be 90% correct. I'm okay with that, but I'm going to give you a 10x problem. How do you think about the next sort of frontier of innovation when it comes to memory? We talk about reinforcement learning as a tool to actually create a better model, but I know that people are using reinforcement learning to actually create a memory system so that they can figure out what to remember, what to recall, what to forget. I'm not sure if this is something that you think about quite a bit, but it is another way that reinforcement learning is making its way into the agentic platform. Maybe tell me some thoughts you have on this.
Yes. So there are several interesting ideas that you said. The first one is, let's allow the reasoning process to have cognitive tools, a memory or a calculator or Python. So that there has been a few papers that said even if you allow a model like DeepSeek R1 Distill to write Python while it's thinking, just to be clear, I'm not asking the model to solve a Python problem. I'm asking it a math problem.
Yeah.
But I can say, you can write Python if you want. If you want to do some matrix multiply, just write Python. And then the moment you write Python, we're going to stop your VLLM execution. We're going to run it through a real Python environment and give you back the answer.
Yeah.
That helped the models.
Yeah.
It gave them, actually, I think I don't remember the number, but significant AME boost. Surprisingly, even if the model doesn't get the answer from a real Python, but it hallucinates the Python output itself, so because you can do that too, right? You can say, write Python and then continue the DeepSeek R1 models from there.
Yeah,
it will produce the answer.
Right.
So it will hallucinate an answer, but surprisingly, even that actually gave a small performance benefit. So thinking in Python and executing it yourself seems to have a small benefit in reasoning, which was very interesting.
I mean, it's almost like just take a break from the problem and do something that has nothing to do with your ultimate answer, but it helps you.
I think it helps it. It doesn't do something that doesn't have to do with the problem because it writes Python that's related to the problem.
Of course.
But maybe it organizes itself in a more principled way, saying, okay, what am I doing? I'm multiplying a matrix with a vector.
That's right.
So now it can invoke other experience on MatMul that it doesn't need to think of it in the context of. Maybe it takes a step back.
Right, of course.
Yeah.
It's almost, it's taking a step back. It's funny how these things work because it starts to make you really think about what we're doing as well, right? You flip a pencil around or you go outside for a moment, you come back and say, I figured it out. But what have you really done, right? I mean, maybe it's just backtracking at the end of the day.
Exactly. So there's one thing is adding cognitive tools, and then the problem is you have to maybe do some RL so the model learns how to use them, or SFT, but usually RL is better for teaching a model how to use tools. And after you do that, you say, oh, let's add the memory. I think a lot of people are working on an external long-term memory tool.
Yes.
Because we also believe, I think, that humans have different memory systems.
Right.
One is, the short-term memory, which is maybe like the context, but there's definitely some other retrieval agent that, as we speak, dumps things into our context and has a subconscious maybe process. So all those extra LLMs or retrieval machines could be running on the background and adding chunks of paragraphs saying, oh, what is being discussed reminds me of this, blah, blah, blah. So these can be thoughts that are added in there, or the model itself can retrieve what you know about the population of Hungary or something. So you could add retrieval mechanisms or calculators, and I think this helps. And the other step that you asked, that is, I think, the frontier right now, is how do you improve the horizon? So we see that agents that have to do tasks that involve 1, 2, 3, 4 steps are pretty reliable. And you can also think of this as time. This corresponds to what the human would do in 10 minutes. But if you say some task that a programmer, for example, or a mathematician, something they can solve in 10 minutes, I think we're already there.
Right.
Now, if you say solve a problem that a PhD student would solve in a day, we're not there.
Right.
So that is where the conversation is. Can you get to, for each specialist, you can say the 10-minute tasks, the 1-hour tasks, and the 8-hour tasks, and then the 1-week tasks. So the real debate is when we'll be able to get to what a human or an expert can do in a day or in a week. And there's different projections, but it's all about the nines of reliability. Because the moment you make a mistake 1 in 100, if you have to do 10 tasks, the probability starts appearing, and then even recovering is another thing. That's when actually another insight I want to add to you is when you're training agents for long horizon, they make mistakes and they fall off the cliff, and the way they fall off the cliff is unique to that agent. This cannot be fixed by SFT, because SFT will show you successful trajectories, but it will never show you how to recover from your mistakes, because your mistakes are unique to you.
That's right.
Whereas reinforcement learning allows you to try. So SFT, you should think of SFT as, here's a math question, here's the solution.
Right.
Okay. You should think of RL, here's a math question, solve it.
Right.
And you come back to the verifier and say, is the answer 51?
Yeah.
And the verifier says yes or no. If it says yes, you get the cookie. Otherwise, you get the bang in the head. And that's
right.
So and then you're like, oh, okay, let me go back and do another rollup. That's the outcome-based rewards. And what we have found, I think DeepSeek R1 showed this to the world, is that outcome-based rewards are sufficient to endow reasoning. Before that, we all thought that you needed process-based rewards, which is like someone looking over your piece of paper as you're writing, saying, that's good, no, you made a mistake. So those intermediate rewards is something we all thought was needed, and they're very, very hard to get.
Right.
But outcome-based rewards are easy because you just check if the answer is correct or if it passes unit tests for code.
Right.
That's why we're seeing so much progress in math and code or multiple choice, because we know if it's right or wrong.
Yeah.
And the moment you get into another domain that's not easily verifiable, that's the frontier.
Yeah.
The point I wanted to make is that the only way to get robustness for agents is reinforcement learning environments, because it allows the agent to make their own special mistakes and learn how to recover from them. Whereas SFT doesn't do this. It only shows you how a wise teacher solves the problem.
So, I mean, while we're on the topic, since you brought it back to reinforcement learning, you started talking about the rewards. This is just from a matter of efficiency and just getting better and better, because obviously RL is this massive frontier, right? We're talking about 8% better than, let's say, SFT, but we're going to want to keep getting better and better. Sparse rewards, dense rewards. Obviously, these are very sparse rewards. You have to be in the vicinity, and every now and then you'll get a cookie, every now and then you'll get a hammer. So how do we start to understand what a dense reward looks, or relatively less sparse reward looks like? How do we get better at that? Or is that not even the game right now?
Yeah. So it depends on the problem.
Yeah.
But what I think is one of the most exciting areas of research is how do you teach agents with something more than a bang in the head and a quickie, right? Intermediate textual feedback.
Right.
The way we have other models that can now, at scale, tell you where you made a mistake. So this more granular way of doing RL, I think, is going to be what pushes the frontier. Because all the ingredients are there. We don't have an algorithm that takes textual feedback and updates weights.
Right.
We have algorithms that take textual feedback and update prompts. For example, you're like, oh, you made a numerical mistake.
Yeah.
I can tell you, make sure you double check all your numerical calculations before you submit the test.
Yeah.
That's an extra instruction in the prompt, and that will mitigate a lot of the numerical mistake errors, for example. But so what people do now is they make prompt optimization. So you can think of RL for optimizing the prompt.
Right.
I'm working on a paper on that with Berkeley students, and I think many other people are working on RL for prompts. It's easier to take textual feedback and update a prompt. We don't have good ways of taking textual feedback and updating weights. We're working on this. And there's several ways by creating specific rewards or several interesting ideas that we're exploring there. And I think that's going to be one of the key ideas to push the frontier.
Yeah, I think the reason I keep asking about this is obviously many companies, DevRev is not an exception, we're going to be spending a lot of money on having data get labeled or information get labeled, right? When you were talking about intermediate rewards or intermediate feedback towards achieving an outcome, or actually turning an outcome into micro outcomes, so you can provide more doses of rewards. And so the sparse reward is not as sparse. What does that look like? Because if you go hire experts in a specific domain and you're like, hey, go label this data or go annotate this information or go help us with rewards or understanding how to annotate some information, they're going to say, okay, how do you want me to do this? and I'm gonna spend 200 hours on this, and you'll pay me for this, and I'll be out. And then if you come back to them and say, okay, actually, no, 6 weeks later, we have a better way for you to do this job that you just did. And we're going to throw that away, and we're going to ask you to do it again. They're going to say, oh, that's fine with me, but you're going to waste a lot of money all year long just getting me to do slightly better versions. Every time there's a slightly new version of what RL, good verifiable rewards look like, or what good rewards look like, period. How do you think this is going to go through 2025, 2026? I mean, because that's what I have to worry about is if I go hire a bunch of experts and actually, or even if I have those experts in-house, if I go ask them or I task them for some period of time to go do this, and this is part of reinforcement learning, what I'm always concerned about is that I'm going to ask them to come back and do it again and again, just because of how fast moving this space is. Like, how do you characterize it? I know you have the benefit of maybe just making the reinforcement techniques get better without having to worry about all the sunk costs. But for people like me, this is a real concern.
Yeah, you're right. You need environments that give you rewards,
right,
so the agent can try different things themselves.
And any improvements therein have to be accretive. It can't be throw all that away. If I have to ask the person to come back and actually do some more labeling, again, all the context in their mind is gone. Right. So they have to start all over again, and they'll just charge me all over again. So how do you think about this?
Yes. One thing that comes in mind is this very interesting paper by UC Berkeley, Stoica and Mert. Mert is the student who led the project, is a taxonomy of how agents fail. And this is focused on multi-agent systems, but I think it's also relevant for single-agent systems. Yeah. Because, as you said, you can say, did you get the cookie or did you get the hammer? But you can also have more granular feedback about, yes, you found the right tool, but you didn't call the right tool with the right parameters. Or you didn't explore this other tool that would have solved it. So instead of saying yes or no, if you make a taxonomy about how agents fail, or multi-agent systems, that is a more granular way, first, to observe what's going on,
right,
and second, to create rewards and improve your system. So I think that a lot of interesting work would be in evaluations or observability tools that look at the trajectories and not only tell you right or wrong, but actually give you a more rich taxonomy of, we see these 5 types of failures. That's another thing is, from a business perspective too, it can tell you, it fails in this way, is that very expensive, or that's the most expensive way, let's fix that first.
Right.
So you get a little bit more nuance to understand how your agent fails.
Yeah.
And I expect a lot of that to be happening. That can happen again with automatic clustering methods that observe trajectories and tell you, this is 10% of your errors are due to this, 50% of the errors the agent doesn't actually call the right tool in the first place.
Okay, so anybody who's listening to this wants a new startup idea, that's a really good one. So if you're looking for a startup idea, that's a good one right there. Thanks to Professor Dimakis right there. We were talking a few minutes ago about Horizon. I'm really interested in this. It's not just about knowing that you should write a program, some Python code, to do something, whether you use it or you don't. We were joking about how it might write the program and not use the program and just end up getting the answer right anyway. What if I not only wanted to write the program? I don't know if you ever played SimCity or any of these games from yesteryear, but it was all about creating something, some asset, some system, some tools, and then using them, right? So, and that's what we've done as humans in civilization. So, if we really want to see agentic value being created, accretive value, eventually what's going to happen is, and this is one of the reasons why I'm primarily very interested in the fact that we're doubling down on code as being one of the areas where we want agents to be excellent. And the reason is because that's a 3D printer. Because once you can start writing code, you can start to create the tools that you need for later on. So you just start to build the software that you need to reference later on. You start to build the tools that you need for later on. Right. And you keep them around. So the keep them around part is part of what a future memory system looks like. You were talking about the capital of Greece and whatnot and keeping that in mind. But the reality is that's interesting from a traditional memory standpoint, but part of memory, and maybe this is just sort of a more expansive view of memory, is to actually have a repository of tools that you're creating, and not just for yourself, but for others. And I think that's how we've created humanity, right? I think this is going to be a big part of having just more and more long horizon tasks be done more efficiently over time. The first is kind of the pioneer task, right? The first agent that had to do problem X, and maybe it was a slightly longer horizon task. and you had to actually not just remember some things and recall some things, but you actually had to create some things. And those things that you created have to be annotated with why you created them and how you created them and what purpose you used them for and whether in hindsight they were useful or not. And you have to actually have that information be collected and stored as a tool or as a skill or whatever you want to call it for others to remember and recall and forget, whatever the case might be. This is really fascinating for me. I think this is what real value creation looks like, right? So that long horizon tasks don't always take as long, right? So you can sort of learn from what's happening, almost like caching what happened somewhere else, or actually looking up what others had done and learning from them and actually reusing some of the pieces that they created along the way. How do you think about that? Maybe it's a little further from what your research is, but at least practically when we're thinking about it, we're always trying to figure out how to bring leverage, right? Do it once and have it be used everywhere. That's the value of creating something really, really good. And so how do we effectively do that, not just as we build agents, but also as we build, as agents build agents or agents build skills?
Yeah. So I really like your question. So I think about this in research. So let me tell you an example. So in chess, for example, when I started learning chess, first you learn how the pieces move. So you think with, okay, I will move my piece, they will move their piece, and so on.
Yeah.
Then you develop new vocabulary.
Right.
You develop the concept of a pin, for example, or a double threat, or it's like actually as you get better and better in chess,
sure,
you encapsulate,
right,
or you package a whole sequence of moves, a pattern, and then you don't think of it as elementary moves anymore. You think of it as a piece of thought, that you have a word for it.
Right.
The same thing happens when we talk about in conversation, the slippery slope, for example, the catch-22. All these things are things that we have names for them, and we have encapsulated an idea, a piece of reasoning, as a tool.
Right.
And now we are invoking catch-22, for example, and we may or may not know what it is. If someone doesn't know, you have to explain it to them, but now they have it packaged in a little API, right? Yeah. So that's a little reasoning packaged API. And another example that I want to give is in research, in math, there's these lemmas that you use to do proofs. So usually, and when I was working with my students, they write complex mathematical proofs. You want to prove a theorem, and a lemma is an intermediate step in this theorem. There is no reason to write a lemma. You could write the whole proof from one end to the other, but the reason you encapsulate those little lemmas is the lemma you believe sometimes is a useful thing outside the proof of the big theorem. For example, the famous lemma is the Johnson-Lindenstrauss lemma that's used in compressed sensing. That was used to prove something that I don't even know what it was used for, but the lemma itself, the gadget, was more useful than the big final product. So the key idea that I have thought about is, can I create such gadgets for reasoning, or let the LLM discover it itself? Right. Induction, for example. Induction is a way to do proofs that's used quite widely. Obviously, it's there in the proofs, but I was thinking of adding meta tags that say the LLM thinks, but then it can add a meta tag, cognitive tool induction begin. So you could annotate things like this, but maybe with RL, you can discover even cognitive tricks that don't have names and start naming them yourself. I think that can only happen with reinforcement learning. Right. Not with SFT, because in SFT, you will only imitate tricks of your teacher, which can be a very, very, very expensive and very, very performing teacher, but only RL will create new tools. Yeah, absolutely. I mean, it's kind of, SFT is like sticking to the curriculum. Exactly. So for sure. No, but I think it's super interesting because, you talked about lemmas and proofs. I think we see this with sort of atoms and molecules and compounds, right? So at some point you stop talking about the specific elements and atoms and you start talking about the compounds, right? Yes. And that's just what we've seen. And just coming back to sort of our empirical evidence, just running a agentic platform at DevRev, we often have people ask us, what is the tool, what is a skill, what is an agent? And the question is overloaded, right? Because the truth is that as agents become more powerful, you won't be able to articulate or enumerate all the tools
Because some of the tools are just going to be generated along the way. And you'll have a lot of tools, and you might supplement the tools with your human-made tools, and the agent might say, I'm less reliant on your human-made tools over the years. Because I just know what you think that tool is exactly what I want. But I have my own version of conjuring it up. And I get to the same result. So I'm going to stop using your tool. But thanks for the idea. And thanks for telling me what your tool does. And I might actually use that. And this is where a reasoning system can actually do that. Something that's been trained to do reasoning can actually develop those skills. So we're quite excited about that. I'm not quite sure how far away we are from that. But I think being able to simulate that in a lab setting and to understand at what point can the agent actually come up with tools that approximate behaviors that human-made tools that are available to it also provide, but it gets better results with its own version. It's kind of like me giving you a knife and you're like, actually, I took a bunch of carbon steel and actually created my own knife, and it actually cuts better than your knife from whatever store you want to say. And I think this is a really, really fascinating subject, but we'll see where things go. Maybe we'll move on from this topic. I do like the idea of model abstraction. We talked a little bit about models creating their own tools, but one thing that is also very interesting from our perspective is, and I guess the reason I'm interested, and this is such a prominent topic for me, is because we're always trying to figure out what does the agentic stack look like. You've got the frontier models, you've got your specific models, you've got, let's say, skills and some sort of a line graph based system on top of that. You've got a RAG based system on top of that. We've created these layers. Everybody wants to reinvent the TCP/IP stack, but in the 2025 version for agentic, right? So everybody show me the 7 layers of the agentic platform. So we get a lot of those kind of inquiries, and we like to discuss it. And obviously people want to see things in that kind of vertical format. But one thing that is fascinating is, and we talked about this a little bit, when I'm trying to do a very simple task, or if I'm doing a very deep task, I'm using the same brain. Now, I might be using different parts of the brain, but I'm using the same brain. Sometimes when we hear about it is, okay, you know what? One of the things that our agentic platform or our system does is use a cheaper model to do this versus it uses a more expensive model or like a 500 billion parameter model for this, and it uses a 14 billion parameter model for this. Do you believe, and I know that a lot of frontier labs are thinking about this, do you believe we're going to get to a point where variable compute, that abstraction makes its way into the models themselves? So they already know, I'm going to spend fewer cycles on this, or I'm going to use cheaper cycles, or I'm going to do more multi-token prediction here, whereas over here I'm going to do single token prediction, I'm going to spend more time and invest more time in reasoning, so on and so forth.
Yeah, it's a great question. Will the model itself decide to do this? MOE models, in a way, choose which part to route to, but they can't adapt size. You could add more logic in the neural network itself to even go to a big network or a small network. But I believe that the way we engineer systems is different than the way that human biological systems have evolved. Like, as you say, human brain can choose to adapt, but human brain had several challenges. When it was evolved, it wasn't the same as how we engineer a bridge or a car or an airplane. The thing that I believe when we engineer an airplane, the airplane doesn't come out of 3D printer. There is different teams who make the wheels, who make the engine, who make the seats. And I believe in that engineering of AI systems. Some people call them compound AI systems, or multiple component AI systems. I think this is how people will build AI systems, not because it's inherently better than a gigantic neural network that could adapt and learn, but because engineers want to collaborate, they want predictability, they want specifications. So there was a paper by Berkeley called Specifications that talks exactly about if you want reliability, you want reasonable costs, and you want also modularity among teams. That's the problem. People have to work together. Right now, the way we train is very monolithic. You just take 1 million questions and answers and you put them in a big pot, you pay $1 million, and out comes this thing, right? And then it's actually very hard to improve a small capability. So I've spent actually some of my time on this. How do you even, you paid $1 million, you got the model, it works, but it just doesn't get this one type of question right.
Yeah.
I don't want to put it again in the pot pay another $1 million. I just want to fix something in there. If I had components that I could get in there and rip something out or measure something, it would be much easier to engineer. So I believe that systems will be engineered with multiple components, which could be small LLMs or an integration of prompting techniques, retrieval methods that populate prompts. They call LLMs, they could call other LLMs, but it would be compound systems, because that's the way you get, I think, specifications, reliability, and also much smaller cost.
And I don't know if you've heard of like the drafter verifier strategy, where you have this sort of cheaper drafter model that just creates a bunch of tokens. I know some of the frontier labs are experimenting with this, but it kind of just creates a bunch of tokens, and then the verifier, which is a more expensive model, looks at it and says, "Hey, you're good. Hey, keep going." So you kind of think of it as asking the intern to do a bunch of work, and you come by and you're like, yeah, you're on the right track, keep going. Right? So it's like you're spending fewer hours on the very expensive lawyer, and you've got the cheap lawyer doing all the work. So
your assistant writing,
exactly.
Drafting.
Exactly. Hence the terminology. And this is really fascinating, because you're seeing this right now. Companies that are trying to put something in front of the industry and saying, this is what state of the art looks like. They're trying to build this into some sort of land graph state model, right? State machine, where they're saying, this is what we do. We just do something simple. We see if it's good enough. And if it's not good enough, then we go through and take further steps. And that's part of our, call it IP or our architecture. I'm not quite sure how defensible that is, because if it was that great, then why would that not go into the compound system? And that compound system is what everybody relies on. Buyers in the industry right now who are trying to buy AI tools, they're trying to figure out what it does a good abstraction look like. But honestly, this is an area that has tremendous flux. I don't know how you think about it, but I think that I would bet on more and more of this making its way into the actual deeper layers of the model.
Yeah, I think there's two parts. Making compound systems with simply prompts and frontier model calls, I think, is a very thin wrapper type of approach, which can go some way, but it's not very defensible.
No, I don't think so.
Right, exactly. I think you have to post-train some components.
Right.
So, Bespoke is a post-training shop, so we're 100% believing that you have to post-train to get real agents to work. I think deep research was the most convincing case for this, because deep research agents are very good.
Yeah.
They're actually hard to get without some post-training, and I think that's one of the examples. And you have to post-train on your own data if you want to have some competitive advantage. But many pieces can be compound prompt calls or other standard things, but you have to fine-tune the magical thing where your data enters. Basically, the moment your data has to enter, it can enter just by retrieval or RAG, which is a very simple way.
Of course.
But the moment you have to think with your data in a non-trivial way, and it's not just, here's an example, do the same as this example, then you have to post-train on your data. And that's where I think the frontier is.
So, I mean, look, you brought up Bespoke a couple of times. I brought up DevRev. We're all doing some very interesting things in this space. And in many cases, we're partnering on some of these things. What are you, maybe we just take a break from sort of my questions. What are you very interested in right now or very excited about? Obviously, I've got a couple of thoughts that I want to bring up, but just as a professor, as a founder, as just an enthusiast in the space, somebody who's a pioneer in many regards, like what are you meaningfully excited about outside of just the fact that this thing is just, spreading like wildfire? Something specific that you're keen on?
I'm very interested in learning about, intelligence. Like, artificial intelligence was even before computer science. I think computer science was created to make thinking brains, thinking machines. So now we are in an exciting time to be alive because for the first time we're cracking intelligence. So on the most fundamental level, I'm interested in cracking intelligence, right? Yeah. So as I said, we crack 10-minute tasks, but we don't crack 1-hour tasks or 1-day tasks. And I mean, if we can, this like scientific discovery, any type of productivity amplification is just incredible in every domain. Everything involved in the physical world is an out ball game. So robotics, this is hard. We're not. Yeah, I don't know anything about that. I know it's hard. But anything having to do with cognitive tasks and coherence of agents is to me extremely interesting. I believe that we're very inefficient now. The reason I believe we're very inefficient, there was this paper training with a single example.
Yes.
So you ask this LLM to solve this problem, the same math problem, some physics, calculate the pressure on the wind, it's some little exercise.
Right.
And the model solves it 1,000 times, there's 1,000 rollouts, and every time it solves it, it still gets a gradient, and it still gets a little bit better. It never gets really good, but the point was, it doesn't learn from by solving one math problem the way a human, like if a human solved the problem once, maybe twice with different solutions, then everything there is to learn about this, every knowledge that is to be absorbed from this problem, you will absorb it by solving it once or twice or 3 times. But the fact that RL is so inefficient that even after 1,000 iterations of resolving the same problem, there's still some gradients, I think showing us that our algorithms are very inefficient. So I think, the way you create these environments, these data sets, and how you learn with RL is what I'm excited about. And there's so many, also impact opportunities in industry, but also core science of how do you make this work.
So I'm glad obviously we've talked about that paper. Could you just maybe name the paper? I remember it was a very prominent one from a month and a half ago.
Training with one example, and then there was another paper that was like training with 0 examples, but all that says is you can ask the model to come up with a question,
That's right.
and then you can verify the answer by majority.
Yeah.
So basically there's a sequence of papers in that space, all of them saying with very few examples and a good verifier, reinforcement learning can go a very long way. And that is true.
I'm glad you brought this up because I wanted to bring up interpretability. And I'm not sure how much you think about mech interp. I know it's a huge space. Are you curious about this area, or is this sort of a pseudoscience?
I think there has been a lot of work for many years, and there has been interpretability work in classical machine learning attributing to training data or to different parts of the model. So there's been model-based or training data-based interpretability papers that have had impact, I think. In reinforcement, like in neural nets, it's very, very hard, and you have to start observing those weights and try to figure out what's going on. I think probably the best way is to have another neural net, observe the weights, tell you what's going on. I'm not sure if we have managed to crack this problem. I think obviously the problem is very important. You can do it with also just data curation techniques or other methods, but observing the weights and trying to learn something out of them is very intriguing, but I don't know if we have solved it. It seems that it's work in progress.
So if we just kind of riff on this a little bit, because I am interested in this sort of sparse autoencoders and just reading about it and trying to understand how it actually works. Do you feel like there is a chicken and egg here? Because obviously you talked about how inefficient these RL algorithms are because you're learning so little, and every time you revisit the same problem, you're able to get a little bit smarter.
Yeah.
Do you feel like if we actually got further with interpretability, that is a necessary condition in actually making a huge step forward in RL algorithms? Or do you feel like we're going to make a huge step forward in RL algorithms anyway, interpretability or not?
I don't think it's necessary.
Okay.
So I don't think that in order to make more efficient learning algorithms, we need better interpretability. And my argument for that is I cannot observe your MRI and know, it's not like I can look in your head and actually get anything out of that, but I can still teach students more effectively than just hitting them on the head with a stick.
That's right. I mean, the number of times we've talked about hitting people, let's just be clear in this podcast. It's a metaphor. We're not pro hitting people on the head. Yeah, but go on.
It's a small, you get 0 reward. Yeah. That's what it is.
Yeah. But please send your kids to Berkeley. Don't worry about this.
No sticks.
Yeah, and they can come work at DevRev. So that's the plug. Yeah, but go on.
It's reward. Yeah, but no. My point is we don't have for humans a very such tools.
Yeah.
We think we do understand when somebody understands something or when they don't.
Yeah.
But we don't do it by looking at their neurons. Sure. Now, of course, it's also more painful to look at their neurons, whereas with neural nets you can look at their neurons without surgery. So it's tempting to you have this, it's sitting there, you could look at it at infinite granularity, Whereas for humans, it is so much work. Even observing a few hundred neurons for people with different, pathologies is so hard, and people do it. And I think it helps for some conditions, but I think it's definitely not a necessary condition. I think if we had good interpretability mechanisms, we could see if the model has learned something. You can say something simple like knowledge editing, right? Or deleting knowledge. Like, okay, who's the CEO of this company? The CEO changed. Now you have to update that. If you could probe the model to see if it truly learned it, that would be valuable. Yeah. Even for something as simple as that.
Yeah.
But overall, it's definitely something that would help, but I don't think it's the only way.
In my mind, it reminds me of like the Human Genome Project to some degree. I don't know, maybe that's just in my head, where you just sort of, if once you've mapped it, you sort of feel like you have a grasp, and maybe that a decade, 2 decades later, that allows for gene editing to be a reality, or at least a thought exercise. And here, this is something that maybe has the same kind of time horizon. But let's say you don't think that it's necessary for reinforcement learning. Do you feel like it's a groundbreaking finding? If we were to get better at it, do you feel like it would help us just get way more efficient with pre-training, post-training, inferencing? That could happen, right? Because then you could effectively say, you know what, this part, this layer, or this attention head is responsible for X, Y, Z. We're gonna, when we do distillation, or when we do quantization, or when we do any of these exercises, latent analysis and so on, we're gonna use that information to actually figure out how to shrink and make the model smaller, or make the model more efficient, or make the model more efficient while it's running in the GPU, so on and so forth.
So I want to say on genetics.
Yeah.
I'm not obviously an expert at all.
Right.
But when I was growing up, I remember we're like, oh, we decoded the human genome.
Yeah.
You'll be able to order your baby, right? Make the eyes blue, make it like have slide bars, like literally control everything, like the height, you want the blue eyes, what do you want, like for control it. So, but I think it was a disappointment. I think that the promise of genetics again, I wasn't in the science of it, but to the layperson, we were all thinking that you'd be able to do so much with genetics. And my understanding is that there are a few conditions that are isolated due to single letter edits that you can check, indeed. But the vast majority of traits and the vast majority of diseases are not predictable, are not easy to edit. So I think genetics has taught us that it's much harder when you're dealing with systems that have gone through evolution.
Yeah.
I think evolution is this blind search, right? And it just adds, you get a little bit of wings, and you get a little bit of a tail, then the tail's gone, then there's a tail again.
Right.
There may be genes that, we had wings, and we lost the wings, and we got wings again. And I think things like this happen.
Yeah.
You carry all these letters that went nowhere. And I think probably in the brain, or even when you're training neural nets, probably things like that are happening too. It starts getting some features about eyes and recognizing different objects, different concepts, and it says, refines them in ways, it learns these representations that are very convoluted.
Yeah.
And I think that's the problem. At least genetics to me would be a warning that, look, you may think you'll be able to look at these characters and know everything, but there's actually very, very few things you can learn. And I think in neural nets too, yes, there are some sparse activations, and you can find, even in cats, wasn't there some neuron for a famous actor or somebody? I think there was some neuroscientist who was recording from the brains of cats. Oh, maybe there was a Casablanca neuron or something.
I did not.
There were some neuroscience papers that could isolate very, very, like there's a single neuron that fires when a specific movie comes up or a specific actor comes up, and so on. So I think some of those things could happen sometimes, but overall, these systems that have gone through evolution or learning with gradient descent are so complicated that I would love it if we can get it, but it could not work. It's possible that, like genetics, most useful behaviors are so baked into this thing that you cannot easily isolate.
Yeah, but still, decades later, you have CRISPR. So there's obviously some developments, right? Similarly, obviously, people have been talking about superposition and things of that nature. So it could help us as we maybe train multimodal models or things of that nature. I think, where there's some co-location in terms of an image and a word that are associated with the same thing. could be co-located in a specific model. And if you see that there's an inclination for that to happen in a model of a certain size, that could help you understand how to maybe create certain types of models or how to do pre-training for certain types of models, so on and so forth. It's a fascinating topic. I do wonder if we continue to invest in that space, or if we have a critical finding in that space between reinforcement learning, just being a better reason model, or being a more efficient model, or any other sort of dimension in which we would benefit majorly. I was just curious to see if you felt like there could be a big breakthrough, but I guess in your mind you're saying we could be very far away from actually having that breakthrough, and maybe it's not worth thinking about what a DAC would actually unlock.
For interpretability, I don't know.
Okay.
But I think for expanding reasoning to longer horizons or specialized tasks, I am super believing that this will happen and can happen. It's just about building environments, having verifiers, and maybe adding reasoning tools, taking on a lot of useful tasks one at a time.
What's next in your eyes? Where are we going with this?
Yeah, I think agents, MCP servers, which allow agents to talk to each other easily, solving verticals and data creation in environments.
Outstanding. Alex, thank you so much. Appreciate your time here. And I think we'll end it here. I think there's a lot more we could be talking about, but this is a perfect time for us to say thank you. And thank you all for watching this. And we'll do this again. What do you think?
Yeah, that's awesome.
Okay, so it'll be a multi-parter. Thanks everyone. Take care.